Hello, myself Kaustubh Dwivedi, and today we are going to discuss about quantum tunneling. And before we go to quantum tunneling, I want to rectify a mistake I did, a silly mistake I did in the last video. So this is what we did in the last video. We were discussing the potential barrier for energy of the particle or energy of the wave is greater than the potential um, the potential barrier itself. So what we did was we did the calculation. All of the derivations were correct. All of the derivations were absolutely correct. But when I was calculating this case, I forgot to discuss this portion. Okay, first. Second is that when I was calculating the RB by TB ratio, RB means the reflection coefficient is to the transmission coefficient of a B stands for a barrier. So when I was calculating this, I forgot to mention this A square. This A square term I forgot to mention. So when till now my derivation in the last video was correct. When I converted lambda square into root over of 2m v naught by h bar square into A, I forgot this A part. So only in the last 1 minute of the derivation you will find this error, and there is something I didn't discuss, is that this lambda into root over of e minus 1, this term is nothing but your K2A. This term is nothing but your what? K2A. These two things which I forgot to discuss. And now we will go to one of the most important part of quantum mechanics, or we say that this is where quantum mechanics will start shocking you. It will start to shock you if you are very indulged into quantum mechanics. I mean, it did shock me when I studied it. That was quantum tunneling. So let's go and discuss that. I have to wipe it out, and I have to make sure that when I edit this video, I will cut this portion out, because it takes time. Wiping takes time. And you don't want anybody to see you wasting time in their video, like that. And okay, it's all done. Today we are going to discuss quantum tunneling. What is quantum tunneling? Quantum tunneling. What is quantum tunneling? Quantum tunneling is basically the analysis of the potential barrier, but in this case, the energy of the wave is less than the potential barrier itself. What happens then? This is your potential barrier. This is your potential barrier. Now let me draw this. Okay, this is 0, this is A. It means it has a boundary. First boundary is at x equal to 0. Second boundary is at x equal to A. And the potential of this point is V naught. Very easy. But now, the wave that is coming to this wave has energy what? Energy E. And here the condition which we are using is E less than V naught. Okay. Remember one thing. When we studied the step potential, where potential was V naught from x equal to 0 to x equal to infinity. We studied a step potential, and there also we did this calculation of E being less than V naught. And what did we find? We find that the transmission coefficient is zero. But we get the probability density of the transmitted wave inside the box or inside the step potential is directly proportional to e to the power minus 2 sigma x. So we can understand why transmission coefficient is 0 in this condition, because this x part is going to infinity. If this x goes to infinity in this step potential, okay, this is doing for what? Step potential and E less than V naught. In this case, the transmission coefficient is 0 because the probability density of the transmission wave is directly proportional to e to the power minus 2 nu x. Nu is our very own what? 2m by h bar square V naught minus E. This is our nu. Okay. Now here for x tends to infinity, t becomes 0, or you can write this as sigma t square equal to 0. That is the reason why we were finding what? Transmission coefficient to be 0. In which condition? In the case of step potential, because this barrier was very long, very big. X goes from 0 to infinity. But in the case of barrier, what happens? The distance is finite. The length of the potential or the length of the potential barrier is not infinite. It is what? It is finite. Now, if we add this term x in this formula, we will find transmission coefficient to be what? Or the probability density of the transmitted wave to be non-zero. Now this is the thing which we are going to test in this question from the beginning to the end. We'll see that okay, this kind of condition is coming out in this case or not. Yes, it is coming out in the step potential, but a step potential has only one boundary at x equal to 0. Let's check that in a two boundary system. In a system that is bounded by two boundaries, let's see what that leads us to. All right, I think we can go. Okay, let me wipe this one because we'll work on this. Okay. Now I'm not going to use Schrödinger equation all over again and do all those steps, or should I? Let me write the part. This is what? Region 1. This is region 2, and this is region 3. Okay. Region 1 means what? The potential is what? 0. So what will we get? We will get psi 1 to be a e to the power I k1x plus b e to the power minus I k1x. How did we find this? I have done derivation of this many times. If you want again, let me do it and I will erase it further. So what we do? We take Schrödinger equation h bar square by 2m del square psi by del x square plus potential. We should use v psi equal to e psi. But in this case the potential is 0 because in this region only the energy of the particle exists. The potential barrier is 0. So v goes to 0. That means we get psi here take psi 1 del square psi equal to 2me by h bar square psi. Now when we solve this equation, you write this part. This 2me by h bar square, you write it as k1 square. Now when we solve this equation differentially, I mean you have seen this equation many times. Those who solve simple harmonic motion, they have also seen this kind of equations. It's a very normal equation in physics. We don't, I mean it's very simple. So that leads us to psi1 to be a e to the power I k1x plus b e to the power minus I k1x. Now this equation, those who have studied, they will know that this equation can be written in terms of a sine and cosine function. Remember this, we use sine and cosine function only in the case of a one-dimensional potential well. Other than that, one-dimensional infinite potential well. In case of that, we use it. Otherwise, we don't. Otherwise, all the time we use this exponential term. Only in case of that, when there is a potential well, or maybe in the case where we have to find the bound states of the system, then we use the sine and cosine part. After this discussion, we will go to the bound state part and we will discuss that. Okay, now I hope you understand how it is happening. I don't need to keep mentioning this. Okay. Those who know this, they will know this very easily, that this part is your incident wave, this part is your reflected wave. So that this wave comes on this potential, and in this region there is two waves which is existing. One is propagating, one is going backward. So now if the point is, if we use momentum operator on psi1, we'll get what? This is state 1. When we add momentum operator on this state, let's say this is psi incident plus momentum operator on psi reflected. Now if we do that, what will we get? What will be the eigenvalue of it? Because P has a value what? Minus I h bar del by del x psi I plus again minus I h bar del by del psi r. Now these two equations will give us what? This will give us eigenvalue h bar k again psi I, plus this will give us what? Eigenvalue minus h bar k. K means k1 on psi r. Now these two tells us that this part, this psi I part, incident part will go along this direction, positive x. This minus h bar k1 will go on the negative direction. That's why it is a reflected wave, this is a incident wave. I hope you understand. Now after this, let's go to the region 2. Let's go to the region 2. What happens in region 2? Okay. In region 2, look, the region 2 for you is a classically forbidden region. Because the energy of the wave is less than the potential. How can it go inside? Okay, let's assume that it goes inside. What will happen if it propagates inside this? First thing first is that it should have a non-zero potential or non-zero momentum. It should have a non-zero momentum. Now, how can we find non-zero momentum when in this case our momentum is measured by what? H bar k1, and k1 stands to be root over of 2m E minus V naught by h bar. H bar goes cancelled. So what is the value of our momentum? Momentum is 2m V naught. Yes. Yes. Now, this is the momentum of the particle inside the region 1. This is using the propagation vector k1. Now, if we use this k1 in this region, will the value of this k1 will be a valid value? It won't be, because E minus V naught will become negative inside, because E is less than V naught. So inside region 2, if we use this k1 value, it will give us a imaginary quantity. It will give us an imaginary quantity. So wait a minute. Okay, yeah. So the recording is happening or not, I was thinking. Okay, let's forget this. Okay, inside the region 2, we will have two more. One is this and another is this. How we found this? Again, same derivation is exactly same. H bar square by 2m del square psi 2 by del x square plus V naught psi equal to E psi. Yes. Now, while deriving this, we can do this. Look, del square psi by del x square we use. We should have written this V minus E minus V naught 2m by h bar square psi equal to 0. But this is an invalid function, because it will give us this form of a wave function, and we'll have the propagation vector to be k1, and this k1 doesn't exist in this region because k1 is coming out to be imaginary. So we'll tilt this. We will tilt this, and it becomes V naught minus E 2m by h bar square. Okay. Now this equation will give us this wave function when we solve it differentially. What happens? This equation becomes nothing but del square psi 2 by del x square minus, if we assume this new to be this, then this equation becomes this. Yes. Now when you solve this equation using differential equation, you will find the solution to be this one. Now in this equation, you can do all that you need. Got it? Yes or no? Got it? Now we have to go to the region 3. Okay, this is psi 2, this is psi 1, region 3. Region 3 will give us what? Region 3 is equal to region 1, because in this region the potential is 0. So what will happen? Exactly this. Only the coefficient will be changed. Let's say f e to the power I k1 x plus g e to the power minus I k1 x. Now what we do in this equation, again very simple thing, we take this part to be at a case where g has to be 0. So what happens is that we don't need a wave in this region which is propagating in the negative x direction. That's why we assume it g to be 0. Okay, that is the condition we take. It's not necessary condition. We take it for the suitability of our calculations. So now if we remove this part here, you have three equations in this part. One is psi 1, one is psi 2, one is psi 3. Yes, psi 1, psi 2, psi 3. Now in every question we do, what we do? We do psi 1 of 0 equal to psi 2 of 0. This is boundary condition at this part. Another thing which we'll do, psi 1 dash 0 equal to psi 2 dash at 0. Dash means d psi 1 by dx. Now look at this. Psi 1 at x equal to 0 will be a plus b. Psi 2 at x equal to 0 will be what? C plus d. A simple condition. Psi 1 dash will be what? I k1 will come out common. It will be a minus b. Here what will come common? It will come on sigma, or sigma no, no, it's nu. Nu will be common. It will be c minus d. For the for the simplicity, we can also write this part as a minus b is equal to nu by I k1 c minus d. All right. This is system. These are two conditions from the boundary condition using x equal to 0, because it is one boundary. There is two equations we find. Then we know we have another boundary. Which one? X equal to a. This is done. Now we'll go to this part. When you go to this part, what will happen? What will happen? Okay. In this region, what you will have to write? Psi 2a must be equal to what? Psi 3a. This condition 1. What that will give you? That will give us, okay, look, psi 2a equal to psi 3a. It is giving us c e to the power nu a plus d e to the power minus nu a equals to what? F e to the power I k1a. Got it? Now you can easily tell it. You can easily say it like what? You can easily say that f is nothing but e to the power minus I k1a whole into c e to the power sigma nu a plus d e to the power minus nu a. Yes, very simple. Now again another boundary condition is psi 2 dash of a equal to psi 3 dash of a. Now what that gives us? That will give us exactly the same thing which we have already found. Sigma you will have to take common. You have to write c e to the power sigma nu into c e to the power nu a minus d e to the power minus nu a equal to what? Psi 3. But in psi 3 you have to take the derivative. So I k1 you have to, if you want to remove this nu, you can divide this nu here. It won't make any change, it won't make any problem, and the equation will be f e to the power I k1a. Hopefully everything is clear here. Yes, I guess so. Everything is clear here. Okay. Can you find C here and D here? Can you find here C and D? If this is one equation, and this is another equation. Can you find C and D here? So you have to add this both equation to get 2C e to the power nu a is equal to, now look at this, if e to the power I k1a can get common, and we will find out what? 1 plus I k1 by nu. Yes? Now that will give you what? It will give you C is equal to f e to the power I k1a into e to the power minus nu a gives rise to, divided by 2 you can also write, this will give us to 1 e to the power I k1 by nu. Similarly, this we can also find D. We can also find what? D to come out f e to the power I k1a e to the power, okay, now in this case we'll have e to the power nu a by 2 plus, when you minus this it will give you 1 minus I k1 rho. So this is the value of C, this is the value of D. This is the value of C, this is the value of D. I hope you understand. I hope you understand this. Now look. Now we have to do very simple math. We have to, okay. Now look at this. We have to use these two conditions and put them here and find the results. Okay. Now what happens? We have to find A plus B, which is equal to C plus D. So in this entire equation, you can take f e to the power I k1a. You can take this common, divided by 2. Now you have to multiply e to the power minus nu a with 1, e to the power nu a with 1. So it will become e to the power nu a plus e to the power minus nu a. Got it? Now in this part, in this two part, you can take I k1 by nu common. Once you take it common, you can write this as, look, you take minus common, so this one will be plus e to the power nu a minus e to the power minus nu a. I hope you got it. After this, you can also write a plus b is equal to, now you have to multiply this 2 with in the inside part, f e to the power I k1a equal to e to the power nu a plus e to the power minus nu a. There is no iota here. So this will lead us to what? 2 cos hyperbolic function. Now 1 by 2 divided with this, which becomes cos hyperbolic nu a, and this part becomes what? I k1 by nu sine hyperbolic nu a. Got it? Now similarly, we have to find a minus b. Now this part will get common. F e to the power I k1a by 2 is common. But when we are calculating a minus b, you will have to take this part also there, because it is nu by I k1 c minus d. It is nu by I k1 c minus d. Now look, this is your c, this is your d. When you calculate c minus d, what is going to happen? First it will be e to the power minus nu a minus e to the power nu a. Got it? Then second part will be, there will be I k1 by nu common, and what will happen when you are doing it minus? It will be minus e to the power minus psi a. Got it? I hope you got it. C minus d is done. C minus d is done. Okay, so this was with plus, sorry. C minus d is done. Now again this can be converted into hyperbolic function a minus b is equal to f e to the power I k1a. Now 2 will be multiplied to it. This one will give us what? This one will give us minus 2 sine hyperbolic nu a divided by 2 I k1. It will give us 2 will cancel. This part will give us 2 cos hyperbolic a. When you multiply this part and this part, this term will be cancelled. So this will give us what? Cos hyperbolic nu a minus what? Minus nu by I k1 sine hyperbolic nu a. Look at this. Exact thing is coming out. Yes. Now this is a minus b. This is a plus b. From this way, what you can find out? You can find 2a. If by adding them, you can find 2a. For finding 2a, you have to take f e to the power I k1a common. What will happen? Cos h nu a 2 cos hyperbolic nu a. Okay, now you have to take what common? Minus sine h nu a. You have to take this common. After taking this common, what is remaining? Nu by I k1 plus I k1 by nu. Nu by I k1 into I k1 by nu. Got it? Now simply what you have to do to find a. A is equal to f e to the power I k1a. Okay, this part when you divide 2, it will become cos h nu a minus in this whole part, take for a moment sine h nu a common, and this entire part will become what? I k1 nu into nu square minus what? Minus k1 square. Nu square minus what? K1 square. Now when you divide 2, you will divide 2 here. So this is the value of a. Got it? Now similarly we can find the value of b. What will be b? Let me write this here. What will be b? Okay. This is a minus b. This is a plus b. From a plus b, you will divide a minus, subtract a minus b. What will you get? So for 2b, let's say b directly, you will have f e to the power I k1a whole into, you have to subtract it. Okay, from this part you have to subtract what? Okay, this part. So now f is coming out to complete common. Now this cos ha will go to 0 because this part will not sustain this part. So cos h nu a is coming out to be 0. Yeah, cos nu a will be 0. This cos I, that cos I will get cancelled. Then you have to take minus I k1 by nu common. What happens then? This is sine. This is sine h nu a. Now this part will become what? Plus nu by I k1 sin h nu a. Yes. Now all of it is divided by 2. All of it is what? Divided by 2. Now b becomes f e to the power I k1 a into sine by 2 into sine h nu a. Here you'll take 2I k1 nu. 2I k1 nu will take. So now this part becomes what? This part will become k1 square and this part will become nu square. That is your value of b. This 2 is multiplied here. This is your b. This is your a. Okay, now what is the thing that we need in all of the equations till now? We need transmission coefficient and reflection coefficient. Yes, we need transmission coefficient and reflection coefficient. Other than that, do we need anything else? Let me check whether it's correct or not, then we will proceed. I have only calculated f. I haven't calculated b at all. Okay, that's why I was saying ki I never calculated b in my notes when I wrote it. I wrote it in this part. I wrote it in 2020. It was in my BSc course. So when I was looking at this formula, I was like, have I ever written this kind of thing? Then it came out in my mind that no, I haven't ever. So let's say A is correct or not. A is coming out to be okay. Have I done some mistake? F e to the I k1 cos sin h nu square. Okay, it's correct. Minus a square. Yeah, it's correct. Very good. Okay. Now what we have to do? As always, what we have to do? We have to find transmission coefficient. This is all we need. Transmission coefficient is what? F star into F by A star into A, which is basically F mod by A mod square. So you have to find F by A square. That's it. And what will that give us? F by A square means what? E to the power minus I k1a by cos h nu a minus sin h nu a nu square by k square nu square by k1 square divided by 2I k1 nu. This square and this square. Yes. Now this square will be complex conjugate of this into this will be 1. So t this will be 1 first. This part will be 1. What is second part? Second part of this square also has to be 1. When you take the square of it, you take minus I for one term, I for one term, that will make it a plus b into a minus b. Yes. Now this will give us cos square nu a plus, because here will be I part. You have to take I square. I square means minus 1. Sin square h nu a, and this term will become nu square minus k1 square by 2 k1 nu whole square. This is your transmission coefficient. This is your transmission coefficient. Now we can simplify it. Let me erase all of it and then I will write it. Okay, now it's clean. Now it's clean. Okay, look at this. Instead of cos square h cos h square nu a, we can write 1 plus sin h square nu a. Yes or no? Yes, we can and we will. So now t becomes 1 by 1 plus, now take sin h square nu a common. That will give us what? That will give us 1 plus nu square minus k1 square whole square divided by 4 k1 square nu square. Got it? Now we can simplify it as this: 1 by 1 plus sin h square nu a. This will give us what? Think about it. A minus b whole square plus 4 a into b will give us, first the LCM will be this, then it will go on top, it will become yes. Are yes or no? Yes. Obviously this is the thing. Now this is our transmission coefficient. This is coming out to be our nothing but our transmission coefficient. That's it. Done. What else? What else is there? Now we will simplify it like in every question. So, okay, let me check whether it's correct or not. I think it's correct. Yes. 1 by square. Yes, correct. Very good. I mean, very good to me, not to anybody else. Okay. Okay, now what is there? This is a transmission coefficient. What we use in this kind of equations? We use E by V naught has to be E. If that is the case, then nu A will give us what? Look, nu A will give us what? Or let's say nu first. Take nu. Nu is our root over of 2m by h bar square V naught minus E. Yes. Now take this common. 2m h bar square V naught. Take that common. What will you get? E minus V naught. Yes, instead of E minus V naught. Okay, another constant we use, which is root over of 2m V naught by h bar square into A. Two conditions we use. Now nu becomes nu, or let's say nu A. Now we can write nu A. Nu A becomes, this term into A is becomes lambda, and this becomes 1 minus E. Yes, this becomes 1 minus E. Once you get here, you can transform this entire equation as, we can also do one more thing if you want. Look, nu square plus k1 square, this gives us what? 2m by h bar square V naught. Yes or no? This is equal to what? This is equal to what? Lambda square by A. Lambda square by A square. Lambda square by A square. Yes or no? Yes, this is lambda square by A square, nothing else. Now 4 into K1 square nu square. This will give us what? 2m h bar square whole square. H bar square whole square. Let's not go there using this part. Will come out differently. We'll stay here, just stay here. You can also write this part as square to be this square is equal to 4 m square by h bar to the power 4 v naught square, and 4 k1 square k2 square is equal to 2m by h bar square whole square. This will give us first 4 into 4 m square h bar to the power 4 e minus v into v. Okay, now take v common. We'll take 16 m square by h bar square. Take v naught common. It will be v naught square into 1 by e. When you divide these two, to get nu square plus k1 square by 4 k square nu square, you will have nothing but (16) okay, this one will be h bar to the power 4, h bar to the power 4 1 minus e. Now m square v naught square m square v naught square h bar cube plus q cancels. 4 cancels with 4. This term now it remains what? 1 by 4 1 minus e. Instead of whole of it, you can write this part. Much easier to write, yes or no? I did this in the last video also. If you remember, I did this in the last video also. This kind of derivations. Okay, if you understand this, I can erase this part. If I erase this part, you will stay with this only. So now transmission coefficient is nothing but 1 plus sine square lambda 1 minus e divided by, instead of this we are writing this 4 into 1 minus e. I hope you got it. Now transmission coefficient, let's calculate. 4 1 minus e equal to 4 1 minus e plus sine square lambda e. This is our what? This is our transmission coefficient in case of quantum tunneling. This is your quantum tunneling transmission coefficient. Hello, so I forgot to do this. So after completing the recording, I have to reshoot again for this part only, because so I shot the video, but this derivation I didn't do. What is the derivation? This transmission coefficient has to be simplified. For the exams, you know, let me just do it. Why I'm talking? Look, this entire thing, you have to find a case. What case? For V naught very much greater than E. Okay. What will happen with this? This will give us E, which is equal to E by V naught. This will be very much less than 1. Okay. First case, first condition. Second condition is when we find lambda. Lambda is our root over of 2m V naught divided by h bar square into A. Now this will be very high or greater than 1. This is condition 1, this is condition 2. Now come to condition 3. What will be the value of this? This will also be very much greater than 1 for this condition. Okay. Now what is the goal here? The goal is to simplify this equation. Now what will happen? Look. Sine hyperbolic lambda 1 minus E root over, this can be written as what? 1 by 2 whole into exponential of lambda 1 minus E plus exponential of minus lambda by 1 minus E. But think about it. If lambda into E 1 minus E is very much greater than 1, this equation, this term is not, if we don't count it, it will be okay, because it will be very much less than 1. So we remove this. We won't even consider it. We will take it here. If this is the case, what is going to happen? For sine hyperbolic square lambda 1 minus E, we are going to get what? 1 by 4 e to the power, what will get? 2 lambda 1 minus E. Correct or not? Correct. Now take this thing and put it here. Take this thing and put it here. What will you get? You will get transmission coefficient will be equal to 1 plus 1 by 4e minus 1. Yes, this is the case first. Second is, now look at this. Instead of sine x square, we can write what? We can write 1 by 4 e to the power 2 lambda 1 minus e and the inverse of it. Yes. Now think about this equation. This term, which is coming out to be here, this part is very much less than 1. Now it is multiplied with e minus 1, which is also what? Very much less than 1. Yes. Now when you have this condition here, this entire equation, this part is very much greater than 1, this part is very much greater than 1, and this part is very much less than 1. but it is in 1 by 2. I mean, it is an inverse place. So what will happen here in this thing? This entire term here is going to be what? It's going to be greater than, much greater than 1. So instead of writing this, we can write is nothing but close to, okay, e to the power 2 lambda 1 minus e divided by 16 e into e minus 1. This inverse. Now what is going to happen? What is going to happen? So that means t for e very much less than v naught, what will you get the transmission coefficient? The transmission coefficient is going to be 16, okay, 16 e into e minus 1 into e to the power, this into inner minus sign. Now this inner minus sign is nothing but your, this inner minus sign, I have already derived this. Let me derive it again. This part, lambda 1 minus e. This part is nothing more than, we can write this as a. We can write this as a into 2m by h bar square v into 1 minus e. Now when you do the multiplication, this becomes 2m h bar square into v minus e. Now tell me, what is this? This is nothing but your nu a. So this will be tunneling, the tunneling coefficient or the transmission coefficient for quantum tunneling is going to be, for e less than v, is going to happen 16 e by v naught into e minus v naught minus 1 into 2 into e to the power minus 2 nu a. Now this part can also be written as what? This part can be written as what? Take v naught common, this becomes v naught square into e minus v naught. 16, it becomes 16 e into e minus v naught divided by v naught square. This is what we need in exams. This is what we need in exams. This formula, you have to remember this formula. I mean, I have to remember this formula because I am also appearing in exams. I need to remember this formula because I remember this. I think I remember this also. It depends. If I revise it, I'll remember. If I don't revise it, I don't remember. To make it easier to revise, I'm eating almonds. Done. Quantum tunneling. This year's Nobel Prize in Physics this year. Quantum tunneling. Okay, good.